two numbers, one object. Astronomers can't agree which is real. Some say Phoenix A star is 5.8 billion solar masses. Some say 100 billion. Almost nobody explains why. The bigger number comes from a galaxy we've never watched stars orbit. The smaller one comes from an X-ray glow. And the black hole everyone calls more precisely measured, TON 618, sits nearly twice as far away. For half a century, TON 618 held the belt. A quasar first logged in 1957 by a small telescope in Mexico that thought it had photographed a star. It had not. The light was 10.4 billion years old, superheated gas, spiraling into a black hole at thousands of kilometers per second, screaming as it died. 40 billion solar masses, some say 66, an event horizon over 1,000 times the Earth-Sun distance. For decades, that was the biggest thing anyone had found. Then, in 2012, a young MIT astronomer named Michael McDonald pointed follow-up observations at a faint bruise in the cosmic microwave background, a shadow 5.8 billion light-years away in the constellation Phoenix. Inside it, 1,000 galaxies, a black hole at the centre, and a central galaxy that should have been dead. It wasn't. It was forming stars at 740 a year. The Milky Way manages 1 or 2. Here's why that number broke the rulebook. Every supermassive black hole studied before this one heated the gas around it, blasted it outward, and starved its own galaxy of new stars. McDonald compared it to coffee. Even a 10 million degree cup cools eventually. The Phoenix cluster was the first cup anyone had ever caught cooling, while the black hole at its centre kept growing. So how big is that black hole? Here's where the two rulers stop agreeing. One estimate treats mass as proportional to the size of the host galaxy, a scaling relationship, not a measurement. Run that math on Phoenix A star and you get 100 billion solar masses. That's the number that went viral. It made Phoenix A star bigger than TON 618, more than double. On paper, the biggest object in the known universe. But in 2019, McDonald went back. Not with a scaling relationship, with direct data, Chandra X-ray, Hubble, the Very Large Array, tracing the actual glow of hot gas feeding the black hole. That number was 5.8 billion, not 100 billion, roughly 5% of the viral figure. That gap, 5.8 billion to 100 billion, is enormous by the standards of the field. M87 star's mass, imaged directly in 2019, carries an uncertainty of roughly plus or minus a billion solar masses. Holm 15A star, another ultramassive black hole at the heart of galaxy cluster Abell 85, comes in around 40 billion with a similarly tight range. Phoenix A star's spread isn't a rounding error, it's a disagreement of nearly 20 to 1, wide enough to swallow every other black hole on the leaderboard inside its own margin of error. So which is correct? To really answer that, you need to know how astronomers weigh a black hole at all, because there isn't one method. There are at least 3, and they don't agree with each other on principle, let alone on Phoenix A star. The gold standard is watching stars orbit. That's how Sagittarius A star, our own galaxy's black hole, got its number. Astronomers tracked individual stars looping around an invisible point for over 2 decades and calculated 4 million solar masses directly from motion alone. In 2022, the Event Horizon Telescope even imaged its silhouette. Real weighing, real picture, both agreeing. One step down is imaging the shadow itself without full orbits. How the Event Horizon Telescope handled M87 star, a black hole close enough and bright enough to photograph in 2019. That measurement, 6.5 billion solar masses, is also considered solid, though less airtight than Sagittarius. a star's decades of tracked stars. Below that, proxies, gas temperature, X-ray brightness, the size of the host galaxy. These aren't weighings, they're inferences built on relationships that hold on average across many galaxies, but aren't guaranteed for any single one. Phoenix, a star's 5.8 billion comes from a proxy. Its 100 billion figure comes from a different proxy. TON 618's 40 to 66 billion figure comes from modelling an accretion disk, a third kind of proxy, applied to a quasar twice as distant and observed with less precision than Phoenix A star. It's treated as more solid purely because it's been repeated for longer. That's not physics. That's seniority. Phoenix A star is too far for stellar orbits and too faint for imaging. No telescope now running can resolve individual stars around it. Until one can, its number will keep swinging between proxies, and whichever proxy gets repeated the most will keep sounding like fact. Which brings us to the ceiling. In 2009, Yale astronomer Priyam Natarajan calculated a hard limit on how large any black hole can get, around 100 billion solar masses. Past that point, she argued, a black hole's own radiation blasts away the gas that feeds it. It starves itself by succeeding. If the high estimate for Phoenix A star is right, it isn't just the biggest black hole we've found, it is sitting exactly on the edge of the biggest black hole physics allows. Starves itself is doing a lot of work in that sentence, and it's worth being precise. A black hole doesn't lose its appetite. It stops growing because its own radiation physically shoves the surrounding gas out of reach faster than gravity can pull it back. The Eddington limit, first worked out for stars, applied here to an entire accretion disk. The black hole isn't full, it's starved by its own glare. And that glare isn't constant. Gas still falls back in occasionally, which is exactly what the newest data shows happening in the Phoenix cluster right now. The ceiling isn't a wall, it's a fight the black hole is mostly, but not always, losing. Not everyone agrees the ceiling is fixed. A newer theoretical class, half-jokingly named stupendously large black holes, pushes the limit to 270 billion solar masses. If a black hole spins fast enough in the same direction as its galaxy. Nobody has ever found one. If Phoenix A star is real at the high estimate, it may be the closest we ever get. In August 2025, the James Webb Space Telescope turned its mirror on the Phoenix cluster, 13 years after McDonald first looked. The new data didn't settle the mass question. It found something else, even more cooling gas, flowing straight toward the black hole. Whatever Phoenix A star actually weighs, it is still feeding, still growing. The measurement problem hasn't gone away. It's just been handed a new decimal to chase. So the honest answer is the one nobody puts in a title. We don't know if Phoenix A star is 5.8 billion suns or 100 billion. We don't know if it's the largest black hole ever measured, or a mid-sized one wearing an inflated number nobody's corrected yet. What we do know is that the biggest black hole in the universe has changed hands 3 times in 15 years, and every single time the correction mattered more than the record. Somewhere between 6 billion and 100 billion suns, something is quietly eating its last meals. We built the ruler. We're still arguing over how to read it.